Hello everyone, and thank you for inviting us to present The New Frontier, AI and Network Multidimensional Printing, and the Architecture, Engineering, and Construction Industry in Space and Deep Sea Settlements, by myself, Thomas Spiegelhalter, and Alfredo Andia. The New Frontier, Building Beyond Earth. Our research highlights two extreme frontiers for the AEC industry, the red plains of Mars and the blue abyss of Earth's oceans. On Mars, we face vacuum, radiation, extreme thermal swings, and abrasive dust. Underwater, we face crushing pressure, corrosion, biofouling, and fragile ecosystems. Across both, a new chapter of architecture and construction is unfolding, driven by two technologies, artificial intelligence and multidimensional additive manufacturing, or ND printing.
A new dawn on Mars. The tracked printer extrudes the regolith, layer by layer, forming the honeycomb structure of our future.
The habitat construction is underway, utilizing wire arc additive manufacturing.
Welding sequence initiated on Section 4. Monitor power fluctuations.
ND printing reshape construction beyond Earth, from early-stage generative design to materials like starcrete to fully autonomous robotic construction and the ethical, legal, and educational questions this raises. AI-driven generative design, the AEC industry is rapidly adopting digital tools. Today, AI sits alongside BIM and parametric modeling, transforming the design studio. We begin with extreme constraints, radiation limits, pressurization, structural loads, and available materials.
Editing straighten. The AI-driven generative design allows us to rapidly iterate through thousands of possibilities.
Developing optimized bionic domes, graded shells, and intricate lattice structures. This process is accelerated by using holographic habitat models as digital twins for scenario modeling and analysis.
The multiphoton lithography rig crafts a sensor-embedded lattice. As the microprobe flexes the structure, the strain-sensing filaments pulse with light.
An autonomous QA drone conducts a LiDAR scan, assessing the habitat's integrity.
The drone conducts a structured light scan, revealing subsurface stress. A localized repair patch is extruded, stabilizing the habitat wall.
Sea vessel and a composite of Earth and Mars. Space logistics and autonomous construction. Launching mass is expensive. We cannot ship bulk cement and steel for every beam and wall. Instead, we ship knowledge and small feedstocks. Printers, robots, and compact biological inputs become the payloads, while the structural mass comes from local regolith, ice, and byproducts. On the surface, autonomous systems immediately begin grading the ground.
Lunar orbit becomes the transfer hub. AI choreographs landers and payloads to streamline a lean, resilient supply chain to the surface.
As the storm intensifies, the autonomous systems activate. Drones deploy protective shielding and electrostatic repellents across the... Abrasive regolith ruins seals and lungs. AI sequences airlock dedusting to keep the base breathing.
Inside the 3D printed lunar habitat, the crew oversees operations. Notice the Earth view and the AI monitoring systems.
The 3D printed lunar habitat provides a safe haven. Our AI Guardian system ensures optimal oxygen.
ISRU and intelligent materials. To truly depend on local materials, we must understand what's in the ground. AI blends orbital and rover data into resource maps that indicate where regolith is printable and where ice is accessible.
From orbit to wheel tracks, AI fuses maps and sensor streams to steer printers toward the best local feedstock. Beneath the rim light, autonomous excavators scrape the shadowed regolith, feeding the ISRU plant. A core drill extracts the vital water ice.
Ice becomes water and propellant. This brings us to starcrete, from potato to structure. Starcrete is a starch-based biocomposite made from Martian or lunar regolith, potato starch, and a pinch of salt. Instead of launching tons of cement, we launch potato seeds and printers. The structural mass comes from the soil. The binder comes from our food system. Lunar starcrete samples are 2 to 3 times stronger than normal concrete. This is a cyber-physical system. Since the starch binder is highly sensitive, sensors monitor the printing process in real time. Machine learning models link this data to performance, and the AI predicts the optimal starch to regolith ratio for each batch, adjusting print speed and local heating to keep the material in the just right zone.
Starcrete rewrites logistics. Instead of launching tons of cement, we launch seeds and knowledge.
Symbiosis and environmental extremes. AI assumes a new role as caretaker inside the habitat. It manages oxygen and dollar text, CO_$2 levels, pressure, temperature, water cycles, and structural health. It can even adjust lighting and acoustics to support crew mental health. This is a sentient building capable of making millions of micro-adjustments, allowing crews to focus on science and exploration.
Inside the 3D printed lunar habitat, the crew oversees operations. Notice the Earth view and the AI monitoring systems.
Sea counterpart, pressure and ecology. Underwater, the environment appears different, but shares a similar autonomous design language. Instead of a vacuum, we contend with immense hydrostatic pressure. Instead of dust, we face salt, corrosion, and biofouling. AUVs and ROVs perform wire arc additive manufacturing, printing metallic shells on the seafloor. AI monitors weld geometry and cooling, adjusting the process to ensure structural integrity under pressure. Inside, AI manages life support, and outside, smart coatings and sensor skins track corrosion. Maintenance AUVs apply protective layers where needed. Different physics, different ecosystems, but a very similar autonomous design language.
The habitat construction is underway. Utilizing wire arc additive manufacturing,
Welding sequence initiated on Section 4. Monitor power fluctuations. Saltwater corrodes, life attaches. Smart coatings and sensor skins keep pressure hulls alive between service windows.
Ethics, and governance. A common design language is emerging across space and deep sea domains. AI-driven generative design, ND printing, continuous sensing, and autonomous repair. To use this language responsibly, we need 3 things. Workforce. A workforce trained in AI, robotics, materials, and ethics, not just drafting. Explainable AI. We must be able to audit why a model changed a life support setting or flagged a defect. Governance. Space law and seabed law are in development. Without clear frameworks, these infrastructures could exacerbate inequality or become instruments of competition.
The deep sea data confirms the viability.
We are integrating the orbital network now.
And the governance protocols are locking into place.
Adoption lags without skills. Hands-on studios teach teams to question, tune, and trust their AI tools.
Conclusion. The AGI metaphor. The future of construction is no longer confined to Earth's surface. It stretches from lunar lava tubes and starcrete domes to adaptive hulls beneath our oceans. We offer a speculative image, a luminous neural lattice connecting Earth's ocean, moon, and Mars.
I want to close with a speculative image.
The future of construction is no longer confined to Earth's surface. It stretches from lava tubes on the moon.
Orchestration across all these systems as a kind of planetary design nervous system. In this final sequence, we visualize AI not as a black box, but as a transparent lattice of decisions, ingesting sensor streams and sending guidance to robot swarms. This is a metaphor, but it raises the right question. If AI becomes more capable and autonomous, how will we ensure that it remains aligned with human values, ecological limits, and a fair distribution of benefits? Our challenge, as designers, engineers, and policymakers, is to ensure that as AI and ND printing expand what we can build, we also expand our sense of responsibility for how, where, and why we build it.